All right, for today's video, we've got a couple different topics. We're going to talk a little bit about limits at infinity, play a little game of what's bigger, and talk about justifying what you're doing on these on these free response questions with calculus. So let's start off down here. We're going to talk about limits at infinity. So when we have rational functions, limits at infinity, we're dealing with x gets really, really big positive or really, really big negative, x approaching infinity or negative infinity. And so the most common type you'll see for these are rational functions, where it's a polynomial on top, polynomial on the bottom. Algebraically, the best way to really justify these is to factor out x on the top and the bottom as much as you can. And if you look at this first example, I can factor out x on the top, and we get 2 over x there. Factor out x squared on the bottom, and we get 2 plus 5 over x squared. And if we were to move forward with this, we would, that x would cancel out with that, and we would be left with limit as x approaches infinity of 3 plus 2 over x over 2 plus 5 over x squared, and all that's times x. Well, if we look at the top now, I'm going to get 2 over x. That x going to infinity means that that term goes to 0. So does this term. But I really still have 3 over 2 times x on the bottom. So this x there means I am still approaching infinity on the bottom. And so I get I get 3 over big positive. That's what I'm thinking there. So my answer to this one is 0. Because if you have a number over a big number, we get 0. In the second example, now we have 5x cubed plus 2x minus 1 over negative 6x cubed minus 3x squared. When I factor out x cubed from both the top and the bottom, they will cancel out completely. And so we are left with the limit as x approaches negative infinity of 5 plus 2 over x squared minus 1 over x cubed all over negative 6 minus 3 over x. And once again, if x is getting really, really big negative, I've got 2 over something big, so that goes to 0, that goes to 0, and that goes to 0. And I'm left with the limit as x approaches negative infinity of 5 over negative 6. And so my answer is negative 5/6. I think in class, a lot of the times we looked at these as really just sort of ignoring the smaller terms. So if we looked at a problem like this one we just did, I know that as x gets really, really big, those lower degree terms aren't going to matter. And this sort of justification would work as well, but really the best algebraic, and it's really not that hard, is factoring out there. Okay, let's play a little game of what's bigger. So sometimes when we're looking at limits at infinity, it's not rational functions. We have to be thinking more about what is actually happening as x gets really, really big. So in number 1 here, we've got x to the 30th over e to the x. It's basically what gets bigger faster. Are we going to have big over small, or are we going to have small over big? And in this case, anytime you have an exponential, it's going to be bigger than power. Exponential is bigger than a power function. So x to the 30th eventually will be much, much smaller than e to the x. So this is really like small over big, which means my answer is 0. Problem like number 2. This one's more kind of thinking about what's actually happening here. And so if I have 2 to the negative x, that's 2 to the negative big, that is more like 1 over 2 to the x. and so this will turn into 0. E to the negative x, as x gets really, really big, this will turn into 0 as well. So here, we just get 3 over 2. And the final point I want to make on this video is a little bit about just some things I'm seeing in your work. Remember, our job here is to justify stuff with calculus. We're not pre-calculus anymore. We are in a calculus class. So like the continuity problems, if there's a free response problem that asks you to determine if a function is continuous at a point, you've got to use that continuity at a point definition where we're talking about continuity at a point, where we're talking about, does the function exist? And don't just say it exists, also talk about what it does it equal, and then does the limit exist as x approaches a. And I'm gonna not be a bad teacher here. We've got to have no naked limits, right? You've got to have something after the limit there. And does the function equal the limit? Okay, so in all these problems, I'm going to be looking for that, and so to make sure you're earning full points on these, make sure you're justifying with calculus and showing work. The whole point of this is to get better at what is the AP test looking for, what do those AP graders want. So as you go through these free response problems today, make sure you're justifying with calculus. There's one you're going to see where you need to do this continuity at a point. You're going to see intermediate value theorem again. Make sure you're talking about, is it continuous over that interval for intermediate value theorem. Some limits. Make sure we're focused on doing this with calculus. All right, that's all. Thanks.